Thanks a lot for inviting me to this extraordinary event. Very impressive. And many talks gave me a lot of food for thinking how can we use all the research that is presented here in the 3D printing industry. And I will speak about the opportunities and challenges of the multi-material 3D printing. I'm leading a team of digital materials in Stratasys. And Stratasys is the biggest worldwide company producing 3D printers and consumables and also software for 3D printers. And actually there are two main divisions. One of them is in the US, and they make the extruder-based printers called FDM. And the division here in Israel are making the PolyJet technology printers, which are based on inkjet. And I will mainly speak on the inkjet printers. So you presented here a lot of research on how you manipulate digital data. And the 3D printers are actually devices that can take this digital data and turn them into the physical world. We can take any kind of digital data and bring it to the physical world in various ways. And I will present you some of them. Now, this research that I'm leading, the digital materials research, it sits on a junction between many different scientific fields. We integrate software and algorithms with materials and chemistry, with system and mechanics and electronics, and also with design. So it's really necessary to combine all these to make some value, to make some serious research in this field. So I will start by explaining you some basics of our technology. The way we print three-dimensional objects is by jetting at least two materials. One, we call it modeling material, and the other is support material. They are jetted from very tiny nozzles, which are somewhat similar to your home inkjet printers, but they're much higher throughput. Actually, they jet about 16,000 droplets for each nozzle per second, and there's about 1,000 nozzles. And that's how a single droplet looks like. It's about 100 microns disk that is actually cured by the UV light that is sitting on the printing block. So we deposit these droplets and we immediately cure them. Actually, they go from liquid to solid immediately, and from the different materials that we can make. And these inkjet printers are the best among the other 3D printing technologies. They're suited the best for multi-material because you can easily put different printing heads and jet different materials. So you can make a black material and you can make a white material, but you can also make a digital material that is actually a mixture of the black and white, and you control this mixture digitally on your computer. It can be just some random mixture or pseudo-random mixture or some arrangement of materials, or it can be some sophisticated code that produce some composite material that maybe mimics some conventionally used composite materials from the materials engineering industry. And we have plenty of different materials that vary in color, transparency, stiffness, performance, water absorption, and even density that can be combined to create new digital materials. And the customer puts different resins in his cabinet, and then from the drop-down list, he can select tens and sometimes hundreds of different materials that can be printed simultaneously and used for the different objects that he creates. And trying to explain the complexity of the digital world we are living in, I must say that 1 cubic millimeter of a printed part will contain about 20,000 object voxels, and the object it's the old name of our technology. And the smallest Lego brick will be composed of 4 million voxels, while full tray will have these enormous number of voxels. So we need to manipulate all this data in order to allow our customers to make use of this capability. And in the end of the day, we say that if the 3D printing brought us the freedom of form, then the multi-material 3D printing brought us freedom of composition. So we can not only generate any form that we want, but we can also control the composition in any tiny volume of this object. And it is now being used for many different products and prototypes. As you know, the 3D printing is mainly used today for prototypes. So every object that you hold, it can be this pointer or this laptop or your iPhone or the car that you are driving or the plane that you are flying. All of them went through a prototyping phase, and about 90% of the prototypes were made using 3D printers. And last month, we released our new 3D printer called J750, which is the first full-color printer that's capable of printing full-color parts. You see this one, it's also printed, and also integrating flexible materials into it, transparent materials into it. So you really have huge material possibilities when using this device. And the way that we combine these different materials together is by creating some microstructures. They can have some ordered phase or some random phases that mix the different materials in various ratios to create the different properties. So if we have a yellow material and the magenta material, we can create obviously the orange and red materials by mixing them in different portions. But we can also create anisotropic properties, parts that behave differently in different directions by mixing the, for example, a soft material and a stiff material in different shapes. So all these cases have the same amount of soft material and hard material, but the way that they are aligned is different, and it will strongly affect the way that they perform. So these three samples have some sandwich structure, all have 50% of soft and 50% of stiff, but they're only oriented in different directions, and you see that the mode of failure of these parts is totally different. And here also you see that they break in completely different ways. And we take it to the limit when we design composite materials that actually mimic the function of conventional composite materials. We take in two components. One is very tough, and the other is very stiff and with very high temperature resistance. Each one of them cannot be used because this one is not stiff enough and this one is not tough enough. But when they are combined, they have some synergistic effect and result in much better properties than you would expect from a general mixing. And it's achieved by a very sophisticated alignment of the different materials over the printed geometry. So we take all this research and we look what are the other uses except the prototypes that we can make with this unique hardware that can actually position droplets, tiny droplets of different materials in any volume that you want. So in the 4D printing project, we collaborated with Scholar Tibbets from MIT, and we created a material that swells in water, and it's the red material here, and another material that is just a stiff material that does not swell in water. So when we print the shape and we put it in water, then actually the red material expands and creates some kind of bending. And we can create structure that can be programmed digitally to go from one shape to other shape. And that's a very simple demonstration of just a linear strand going to some cube. And then we made other demonstrations of more sophisticated three-dimensional structures going from one form to other form just by programming how you position the material that swells and the other material that remains static. And all these use a lot of programming and a lot of simulation software to allow the designer to generate these geometries and to program what the transformation will look like. And when we go even further and we don't want to just limit ourselves to distinct areas assigned with specific materials and working only with ordered materials, we want also to enable complete free form of gradients of any materials that we want. We developed a module that we called voxel print, where we enable the user, instead of just assigning a specific material to a volume represented by a mesh, we allow the user to send directly bitmaps that correspond to each droplet that is being printed. So we can actually program our printer to maximize the capabilities and control every little piece of the geometry that he prints. So you can make gradients in any transition that you like. And that's a kind of experimental interface that we currently provide only to research institutes. And it requires from the users to use some programming language, some MATLAB or C++, or generate their own modules that will output these bitmaps, because today we don't have enough tools that allow volumetric painting and creating some volumetric raster structures. But in the recent years, we see more and more works that are being developing such tools. And one of the labs that we are working tightly with is Neri Oxman lab from MIT Media Lab. Neri Oxman studied architecture here in Technion and now leads a very high-end laboratory in the MIT. And this research is talking about a prosthetic socket that says that a limb is actually non-homogeneous. It has some areas that are harder and some areas that are softer, and we could benefit from making a socket that will provide a softer support in the harder areas of the limb and harder support in the soft areas of the limb. So this research actually generated raster data that corresponds to the limb heterogeneity and to the limb stiffness in the different areas. And it was printed with our Tango Plus material, which is a rubber-like material and a stiff material, and actually created very interesting heterogeneous structure. And you can look for there is an article on this subject. And there was much work that we did with Neri in the various fields, in art, fashion, and design. And you can see some of it. You can see the very sophisticated material heterogeneity that was created in these parts. And she was working with Craig, with other professors who generated code that created these models. But recently, she started working with two guys, Christopher and Dominic, from Descriptive, who created algorithms that actually grow structures. They grow structures and they grow multi-material structures. So you guys obviously are familiar with these technologies, how this stuff is made. I'm more on the chemistry side, so I just make use of these tools to combine our different materials and create, to see how we can take it to the limit and create something that was not possible before, and also to see if we can make this multi-material printing more accessible to the regular users. And since these algorithms are controlled by parameters, you can think of simple GUI where you can just change some parameters and create very sophisticated forms. And indeed, these algorithms were used for the Wanderers project, where these forms were generated and then printed on our printers, and we added not only the sophistication of properties and color, but also transparency. So you can see the different material variations that were created in this project, and it was really stunning to see these coming out of the printer. We send it just bitmaps, and we don't know what will come out. And you watch the part, and you are just amazed by the things that we created. And I think that the most interesting thing was printing this part also with internal channels and putting inside some bacteria that makes photosynthesis and glowing in the dark. So it's a kind of combination of biology and 3D printing and algorithmics. And you can read more about it. And there is a nice movie showing this project that I don't have time to go into it. So these projects were doing some imaginary shapes, but we took this and we look how we can take it down to earth and to use it to mimic not imaginary shapes, but our own bodies, which are highly heterogeneous. They can composed of many different tissues with many different properties. And we now have the capability to take some medical scan data and some biological data and convert it into printable data, where we can generate, for example, a printed hand from a city data directly without even going through a mesh, because a city data is a kind of 3D raster data, and it's very similar to the data that we print. We can take the city data and convert it very easily to printable data. And you can see here that if this is a city data, so and this is a case where you separated two shells, two different shells of bone and flesh, and you see that you lose a lot of information in the cartilage, for example. But if you don't go through a mesh and you don't do any threshold, but you convert the city data directly to a printed data, you can actually preserve all the slight variations of the tissue densities that are in our body, and create this highly sophisticated organs. And we also learn a lot from the computer graphics world, which already understand how, for example, human skin reflects light, and what are the algorithms that you need to employ to simulate a realistic appearance of human skin. And we take this understanding and we put it into our materials. So we develop materials that actually scatter the light in a way that's very similar to human skin, and we can generate also the flesh that also have properties that are very similar to the soft tissues of the human body. And we also employ some bump maps. It's all techniques that are taken from the computer graphics into 3D printing, and it results in things like this. For example, this is a printed hand that has an internal structure of all the bones and ligaments, and it has a red flesh, and it's covered by opaque skin material. And it really represents, in a very sophisticated manner, the appearance of a real human organs. Yeah, so I will finish here, and I just say that we're really looking for more and more tools from computer graphics and from algorithmics to make our system run faster, to make more sophisticated objects, to make it more accessible to the people, and to bring the multi-material 3D printing to all of us. Thank you.